Hello everybody, welcome to today's video. We are finally exiting the college algebra portion of the class and we are going to start talking about trigonometry now. So today we are getting into it with angles. So we will look at drawing angles in standard position if we know the degrees. And then we'll look at radians, maybe a new unit of measurement for you when we're talking about the measure of an angle. We'll talk about how to convert between degrees and radians. We'll look at what a coterminal angle is and what a reference angle is. And then we'll talk about the arc length of a sector. If we know the measure of the angle that creates it and the length of the radius, then we can find the measure of that arc length. So we'll first start off with just kind of a bunch of definitions here leading up to angles in standard position. So the first thing we want to look at is a ray. An array is a directed line segment, meaning it's got some end point here, and we will call that the end point. So that's the first point here, and then it's directed in some direction and it'll go off, infinitely over there, and we can refer to a specific ray by stating its endpoint and any other point. So on this ray here we have an endpoint of E, we have another point F, and we can call this the ray EF, or as it says on here, just ray EF. An angle, so moving on to the next one here, is the union of two rays having a common endpoint. So you can see here both of these rays have a common endpoint. At E we have the ray EF, and we have the ray ED. And we can take those two rays, since they have a common endpoint, and make an angle out of this. And we could say that this is angle DEF. So over here, it's writing the word angle. I'm using the symbol for angle in here. But it could go the other way too. We could say that this is also angle FED. Those say the same thing, just depending on where we're starting at. As long as the vertex is in the middle, that is what is important for us here. There we've got the endpoint. It's called the vertex of the angle, so we mentioned that. And then the two rays are the sides of the angle, so each one of the rays is a different side of the angle, and they actually will have more specific names here. As we now take that angle in standard position, means that we're going to fix it onto the axes here, the XY plane. And we're going to fix one of the sides to the x-axis here, and we will call that the initial side. So there we've got the initial side fixed to the x-axis, and then the other ray is going to be called the terminal side, and that's usually kind of what we view as maybe the one that is rotating around the coordinates here. But we call that the terminal side. So the initial side is fixed to the x-axis, and the other one that can kind of range here is called the terminal side. And then what we're often looking for is the measure of this angle. And we usually denote it with some sort of Greek letter. So here I've got a theta. So this is how you say this. That's a theta. And it tells us the amount of rotation from the initial side to the terminal side. So the most familiar angle I think that we are used to is the degree, and that just breaks a full circle, so a full rotation, into 360 parts. So we see here that 1 degree is equal to 1 over 360, and you might think, why would you break a full rotation into 360 parts? It seems like kind of an arbitrary choice. Well, there were cultures that worked in base 60 as they were developing their number systems, and so 60 squared is 360. So breaking something into 360 pieces for them is as natural as us breaking something into 100 pieces, since we work in base 10. 10 squared is 100, so to them breaking a circle into 360 pieces was very natural. So presumably that is why we have that there. But it is what we most often use, is just breaking a full rotation into 360 pieces. Some other common variables that I have listed down here that we use for angles. So there's a theta there, and maybe I'll write in the names of these as I'm going through them. So the first one here is a theta. That's this guy here. This one is a phi or phi, and that is a lowercase. There's also uppercase, which we might see as we go. The next one here is an alpha. So there's the alpha. This is a beta. And then the last one here is called gamma. And these are just different Greek symbols that we use to talk about the names of these angles. That way we can somewhat differentiate between if we're talking about some radius or the length of a ray or a line segment. We can use things like x and y for that, and then we can use things like alpha or theta for our angles. That way we have some sort of indication on what we're looking for, if we're looking for a length or an angle measure or what. So there we have just some basic definitions to get us going here. We want to be mostly looking at angles in standard position. So we'll take whatever angle we have, we'll fix it to the coordinate system, we'll make sure that one side is fixed to the x-axis, and then we can measure the other side by looking at how far it's traveling around the coordinate system here. So let's take a look at some common angles in standard position. Using some things hopefully you know from geometry, it looks like if I'm going to fix an initial side here, do my best to get that kind of close. Wasn't that great, so I'll just draw a freehand one here. There's my initial side, and hopefully what you know from geometry in high school is that should make a 90-degree angle. So this should give us 90 degrees up here. We can call this 0 degrees over here. If the angle hasn't moved at all, or if the terminal side hasn't moved at all, then it's moved to 0, so that would be 0 degrees. And we can think about just breaking just this quarter segment up into smaller pieces. So just the whole circle is already broken up into 360. So we could break this up further. In fact, maybe before we do that, let's investigate the rest of the entire circle here. So if we think about this entire straight line all the way across, or thinking about this angle here, hopefully you know that a straight angle is 180 degrees. It's just a straight line. So this first one in yellow here gives us the 90 degrees. This one in green gives us the 180 degrees. Let's look at what happens if we come all the way around to this other side here. Well, we've got 80 degrees, and then we went another 90 degrees, which is going to give us 270 degrees down here. So those are some common angles, and then I think, as we mentioned, the way that we even define this is by saying, okay, there's 360 degrees in a full rotation, and then we can kind of break things down from there. So there are the main 4, or I guess 5 if you want to count 0 and 360, but usually we choose one. We either want that to be 0 or want that to be 360. But those are the main ones, that kind of the main quadrants as we go around. Now let's go and think about just breaking this up even further within each of these quadrants. And we do refer to these as quadrants, so maybe I'll take a second to remind you of that. But we would call, get some colors here. This is quadrant 1. Over here is where everything is positive. The x values are positive, the y values are positive. Over here is quadrant 2. This is where the x values are negative, but the y values are positive. Over here we have quadrant 3. This is where everything's negative, both x and y are negative. And then we have quadrant 4. Over here the x values are positive, but the y values are negative. So I want to just think, in each of these quadrants, can we find some other nice angles to look at? And we could take, if I'm looking at this first 90-degree section here, I could split that right in half. So I could always just split it in half, and this is going to give me, 90 divided by half is 45 degrees. So we've got a 45-degree angle there. We could also split 90 degrees into thirds. Since 90 is divisible by 3, we could also split it into thirds. So if I just do a third of the way to 90 degrees, 1/3 of 90 degrees is 30 degrees. So kind of a third of the way to 90 degrees, we should get 30 degrees. And similarly, if I go 2/3 of the way to 90 degrees, we will get 60 degrees. So there we've got some of the more common angles around this first quadrant here. So 30 and 60 are thirds, 1/3 and 2/3 the way around. And then we've got 45 degrees as being halfway from 0 to 90 degrees. And we can play the same game all the way around as we go. So if I'm thinking about what we have over here, if I go halfway through quadrant 2, what sort of angle measure is that? Well, we've got 90 degrees, and then we went another 45 degrees. Let me move the quadrant 2 symbol out of the way. We went another 45 degrees. So 90 plus 45 is going to give us 135 degrees total here. And let me erase my little scratch work. So we're always thinking about breaking each one of these quadrants either into half or into thirds so that we can get some other common angles in here. Oh, I guess I switched my colors, but that's okay. So we'll do the other ones in green here, I guess. So if I only go a third of the way from 90 to 180, well, I just want to add 30 to move 30 more degrees, and that's going to give me 120 degrees. If I wanted to move another 60 to get, whoops, I didn't want to erase, another 60 to get this angle over here, that's going to be the 90 I already moved from here to here, plus another 60 degrees. And 90 plus 60 is going to give us 150 degrees. So here we are starting to build all of the common angles as we go around here. Maybe just to quickly fill in the rest of what we've got, if I want to get halfway around quadrant 3, from quadrant 2 to quadrant 3, or I'm sorry, yeah, from quadrant 3 to quadrant 4. Let me just move this out of the way. Now this is going to be 180 plus 45 degrees is going to give us 225 degrees here. So that is the halfway angle. And then if we want to look at the third of the way through quadrant 3 and 2/3 of the way through quadrant 3, that's going to give us 210. That's 180 plus 30. And then this will be 240 on this side. And then if we want halfway through quadrant 4, get that out, oops, that out of the way a little bit. If we want to go halfway through quadrant 4, then that's going to be 45 plus 270, should give me 315 degrees, which means that just a third of the way through this one, add another 30 to 270, and we'll get 300 degrees. And then looking 2/3 of the way through here should give us 330 degrees. So there we go. We've got a lot of the most common angles, the ones that are at least kind of somewhat easy to find as we go around here. By just thinking about, okay, if I break each quadrant into 90 degrees, I can then move another 45, I can move another 30, I can move another 60 to kind of find all of these common values here. Now, as we work, you will probably end up memorizing a lot of these values, but at least knowing this first quadrant can help you figure out the rest of the quadrants by just thinking about moving that 1/3, moving that 1/2, moving that 2/3 more than these big 90-degree angles. So there we've got all the, not all of them, but a lot of the common angles in standard position. All right, moving on here, we'll take a look at just trying to sketch in some angles in standard position. So some of these we just saw, and some of them are negative, which we didn't talk about. Well, we can talk about what that means right now. So the first question is asking us to sketch a degree sketch an angle of 30 degrees. So I've got the axis here, and I've just got this circle just so that we can make some references, just like we did on the previous page. We didn't need that circle in there. Maybe I should have started off by mentioning that circle. It's just there to give us some sort of reference, so I know kind of where to mark. Where does halfway live around of breaking this circle up? Where is halfway? Where is a third? And I think that's the one that we want for this one, is I'm going to break my 90 degrees into thirds, and so I'm just kind of looking where is about a third of the way to 90 degrees in this first quadrant. And it's around there, so I will just connect there, and I'll say here we've got our angle theta is equal to 30 degrees. So it doesn't have to be perfect, but we can at least sketch that in there somewhere close where we know it's supposed to go. All right, for this next one, we want to sketch an angle of 135 degrees. Well, I know 90 degrees is up here. So at some point you might have this one memorized, and maybe you already know where it is, and that's great. But if we're trying to kind of build this from scratch, well, I'm thinking, okay, I'm going to go at least 90 degrees here. And then I need to go how much more? Another 45 degrees. And I know where that is. That's about halfway, or it is exactly halfway around quadrant 2 here. So now I can make my angle here, and I can put in, usually we'll draw these little arrows to indicate that that's where the angle is, and theta for this angle is 135 degrees. Maybe I should have done a little arrow on that guy too. So there we've got our angles, and maybe I'll draw on the initial sides as well, just to be like real clear where that angle is. Okay, so there's drawing in some quick sketches of some positive angles, but let's talk about these negative angles. So notice that when we were talking about positive angles, we were moving counterclockwise around the axes here, and that's just the way that things are defined and the way that we do it. But if I want to move in the negative direction, well, I'll just go the other way. So I'll just say if we're going to move this way, then that's going to be positive, and if we want to move down, that's going to correspond to negative. So here we want to go negative 60 degrees. So I'm going to think about breaking the fourth quadrant here into thirds, and I want to go 2/3 the way around. If this is negative 90 degrees down here, then I just want to go negative 60. So that's 2/3 of the way there. Whoops. So I'll mark just kind of where around 2/3 of the way to negative 90 is, and then I'll draw in my angle, and I'll draw in my initial side just to make it real clear. Maybe I need to sketch it in. So this angle here is going to be theta equals negative 60 degrees. And then lastly, we want to do a sketch of negative 330 degrees. So thinking about that here, we're again going to be moving in the negative direction. So this is going to give me negative 90. If I go another 90, we'll have negative 180. If I go another 90, we'll be at negative 270. If I go all the way around, I'd be at negative 360, and that would be too far. But I just want to go 60 more. So if I think about breaking this first quadrant into thirds, and I'm coming in from the other direction, so I'm thinking about going 2/3 of the way from negative 270 to negative 360. Then that will be around there. So now I'll draw in, I'll draw in my angle here. And to be real clear, let me just draw in, I meant to grab the eraser. Let me just draw in what this angle is, and it is going all the way around like that. This is the angle, theta equals negative 330 degrees. So I can get rid of some of these extra marks that I put on here as we went around. But there it is. I've got my angles sketched in here. So positive, we move counterclockwise. For negative angles, we move clockwise. We always start at the x-axis, at least if we're in standard position. Maybe later on we're going to look at an application problem where we won't be exactly in standard position, but we can still think about things the same way. All right, it is time to talk about radians. Now that we are somewhat comfortable with degrees and where that kind of lives as we mark them here, we want to talk about radians, which is a perhaps new unit of measurement for you to measure the angle, the measure of an angle. And the way that we define this is, and I'll try and unpack this as I'm reading it because this is a very mathy sounding definition, but an angle in standard position, so this is kind of our example that we'll be looking at here. Here's an angle in standard position that intercepts the arc of a circle. So here we can see that it's got a couple of sides here that are intercepting a circle with the length equal to the radius of the circle. So here what we're seeing is that this has a radius. Let me get rid of everything I've scribbled on here. This has a radius of r right here. And we're seeing that the arc length that's been swept out by this angle is also equal to r. So we're using s to denote the arc length. And here we can see that the arc length that's being swept out is equal to the radius. That means that this angle measure is 1 radian. That is precisely how we are defining 1 radian, is that it is the angle that is created by sweeping out 1 radius of an arc length. So radius, radian, hopefully you notice the connection there. And so this is just another way that we could define how to measure an angle, and we'll discover that this has actually a lot of nice properties, and we can use it in ways that we can't usually use degrees. And it'll be a very helpful thing. In trigonometry, we usually do things in radians, and at some point you will forget that degrees even exist because radians will become your new best friend. But let's spend some time thinking a little bit more about what they are here. So for these other two examples, and let me get rid of more of my scribbles again. So looking at this next here, we're asked to find theta. And here we can see that what is being swept out is 2 r's. So we're going a distance of r, and then we're going another distance of r. And we're told that this arc length here is 2r. So if we want to know what the radius, the radian measure is, well, we need to break that distance into however many radians it just went. So if it traveled a distance of 2 radiuses, then we need to divide that by the radius, and we'll see that the angle measure here is theta equals 2 radians. And I'll just write rad for right now, but you might notice at the bottom of this page here it says, note, unlike degrees, radians are a unitless measure. So we'll talk about that in a minute, and we'll talk about why we don't actually need to write rad at the end, because radians have no unit, and that is one of the reasons why they will be so helpful moving forward. So let's think about this a little bit more, because I think it still can be even a little confusing at this point. But this next one here has a little bit more to it. We've got some, there's a random 2 there. We've got some actual numbers plugged in here. So what we're saying is that as we travel around and we look at this distance, that is a distance of 8. And I'm not writing a unit on here, but we're going to talk about units in a minute. And that is just some distance of 8, and we see that the radius here has a measure of 2. So what this is saying is that if I break this distance up, then that's going to be a distance of 2. And then over here, that's going to be another distance of 2. And then over here, that'll be another distance of 2. And then for this last bit here, that's another distance of 2. We know that since the radius is 2 and that arc length is 8, that we can fit 4 of those radius in there. So that tells us that this radian measure, this angle measure here, we can take the distance of that arc length and divide it by the number of radiuses that are in there, which in this case is a length of 2, gives us 4. I think I said that backwards. But we can take the length of that, the arc length, we can divide it by the length of the radius, and that'll tell us how many radiuses fit in that arc length, or the number of radians. So here there are 4 radiuses fit in that arc length, which tells us that this has a measure of 4 radians. And I won't write radians because it is a unitless measure. So we'll talk about that now. Unlike degrees, which have a measure, which have a unit of degrees, we usually write the little degree symbol on there. Radians are a unitless measure, which means there is no unit to speak of, which is maybe a weird thing. Maybe the first time we've seen something that has no unit attached to it. So if we look at this third example we did up here, and if we say that things are in feet, if I said that this was 8 feet and this was 2 feet, then as I'm trying to compute the radians here, I would do 8 feet divided by 2 feet. And when we think about doing unit conversions, which hopefully you've practiced before, we can think about canceling out the units. We would literally cancel out feet over feet because we're dividing that. Feet over feet would just give us 1. We don't need to write it. So this is going to give us 8 divided by 2, which is just 4. And there is no unit to write, like literally unitless. There is nothing to write next to it there. So hopefully that gives you maybe a little bit more of a convincing argument for why this would have no unit. But like I said, we're going to be using radians a lot more, and the fact that they have no units will be very helpful to us. All right, moving on. Maybe a natural question that you want to ask is, how many radians are in a full circle? We know there's 360 degrees in a full circle, but how many radians are in a full circle? Well, since we have that the angle in radians is defined by the ratio of the arc length to the radius, that's what we saw over here, and we were doing in all of these. We were taking the ratio of the arc length to the radius, the ratio of the arc length to the radius. So that's how we define the radian here. So since this is the way that we define it, as the ratio of the arc length to the radius, let's look at an arc length of an entire circle. So if I want to look at 360 degrees, that means we're going to travel all the way around and complete a full 360 degrees. We know that the formula hopefully, for circumference is 2 pi times the radius. That is the formula for circumference. And we have this over the radius. If we just do a little simple algebra here, r over r just gives us 1. We are left with just 2 pi. So there are 2 pi radians in a full rotation. So we can say that 360 degrees is equal to 2 pi. And again, we don't need to write radians. I just wanted to get that in there to be a little bit clear. So let's think about breaking this up even further. If 360 degrees is 2 pi, then 180 degrees, which is half of 360, well, that must mean that it is half of 2 pi, which means that 180 degrees must be just pi. So here we have a measure of just pi, radian measure. So what we're seeing here is that 180 degrees is equal to pi, and we're actually going to use this a lot to our advantage as we go forward. Okay, well, let's think about just moving 90 degrees then, if we have just this rotation of 90 degrees. Well, here we know that 180 degrees is pi. 90 is just half of 180 degrees. So that's going to be pi over 2. No simplification to do there. We just straight up get pi over 2. So if we're looking at this angle here, 90 degrees is the same as pi over 2. And then we could also look at maybe the forgotten about one here, but if we go 3/4 of the way around, this is the same as 270 degrees, which is, if we think about it, 1 pi over 2, 2 pi over 2, 3 pi over 2. I'm just counting pi over 2s. Now that I know 90 degrees is pi over 2, there are 3 pi over 2s to get there. Different ways that maybe we can think about that, and we'll have a nice formula to make that conversion as well. But here are kind of the big four in terms of radians for or radian measure, that 360 degrees, same as 2 pi, 180 degrees, the same as pi, 90 degrees, the same as pi over 2, and then 270, 3 pi over 2. All right, taking a look, like we did before, we looked at common angles in degrees. I want to look at common angles in radians here as well. So I've got those big ones put back on here for us. So 0 and 2 pi over here. Let me change my color. 0 or 2 pi, depending on if the angle has not been created or if it's gone all the way around. We can either consider that 0 or 2 pi. We've got pi over 2 here, pi, and then 3 pi over 2 down at the bottom. So let's think about splitting these up again, and for now we're just going to focus on this first quadrant, breaking this apart. So again, we know that 45 degrees would be right smack dab in the middle there, and so if I'm just thinking about taking this 90 degree angle and splitting it in half, we know that's 45 degrees, but now I want to take pi over 2 and multiply it by 1/2. And this is going to give us pi over 4. So here we can see that pi over 4 is the same as 45 degrees, but knowing that that's a radian measure of pi over 4 will be very, very, very helpful to us as we move forward. And then we can think about those third of the way around as well. We know that this would, in degrees, be 30 degrees. That's a third of the way to 90 degrees. So it's also a third of the way to pi over 2. A third of the way to pi over 2, which is going to give us pi over 6. So that is a radian measure here of pi over 6. And then we can do the same thing with that 2/3 the way around. So 2/3 of the way to 90 degrees, 2/3 of the way to pi over 2 is going to give us pi over 3. So there are kind of the big players here, at least in that first quadrant, and we can kind of do what we were doing before of, okay, now if I'm at pi over 2 and I want to go 45 more degrees, then what's that going to be? Well, that's going to be pi over 2 plus pi over 4, which is going to give us 3 pi over 4. I also could have just counted 1 pi over 4, 2 pi over 4s, 3 pi over 4s. So there's a lot of different ways to think about getting all of these angles here. I won't go through and fill out the entire list like we did last time. It is a bit more tedious, but I will just show you a list of all of them here. So if you would like to write them all down at this point, you can pause the video and write them down. But I think the more and more you do and the more and more you practice, that these will just get memorized. I don't recommend, you know, sitting down and making flashcards and trying to memorize these. But I think as you do homework problems and as we do more with angles and as we do more with radians, you will just get these more and more ingrained into your head. But I think knowing at least these three in the first quadrant here, knowing how those correspond will help you to be able to figure out anything else that's going on in any of the other quadrants. So yeah, here's just all the common angles in both degrees and radians. I think that this is helpful to see. As we move forward and talk about the unit circle in a future video, in a future lesson, we'll see the same picture pop up again, but then we'll start talking more about it. So this isn't necessarily the unit circle by itself. We have nothing to tell us that there's anything unit about this, which means that it would have a radius of 1. But we will be using the unit circle in the future, and at least having this, being comfortable with all of these angle measures will be very helpful as we move into that. All right, we will now talk about converting between degrees and radians. So we will see going forward that radians are what we're going to want to use in order to, you know, just do certain things, evaluate trig functions. We're going to use it later to figure out an arc length, but we need to know the degree, the measure in radians and not degrees. So being able to convert from degrees to radians will be very helpful. It will also be helpful to convert back from radians to degrees if we do have some sort of application where we need to know the degrees. So here is just a relationship. Remember that 180 degrees and pi are the same measurement here. So we're just setting up this direct proportion that if we have some amount of angle in degrees being compared to 180 is going to be the same angle in radians compared to pi. So hopefully that proportion makes sense. Since 180 and pi are the same, we're just setting up this proportion to have the same values. We should always know at least one of either the measure in degrees or the measure in radians. So let's use that here. We'll put this to work. This first one, we have 210 degrees and we want to convert this into radians. So I'm going to set up this proportion here. This says 210 degrees over 180 degrees is equal to theta r, which is going to be our measure in radians. So that is the difference here. This is just notation that the angle is going to be in radians, and this is notation that the measure is going to be in degrees. And we'll put that over pi. So we want to solve for theta sub r in this case. So what we're going to do is multiply both sides by pi. We're doing that, so on the right-hand side they cancel, and we're just left with theta. On the left-hand side, we can actually think about the degrees canceling as well. Remember that this should be a unitless measure when we're done. So at this point, I've got theta sub r is equal to 210 pi over 180. I can reduce that a little bit to get, oops, not 2 pi, but 21 pi over 18. 3 goes into both of those, and that'll give me 7 pi over 6. So this is the radian equivalent, 7 pi over 6, to 210 degrees. All right, let's take a look at this next one here. We want to do negative 135 degrees and convert that into radians. So we will do set up our proportion here. Negative 135 degrees is to 180 degrees. What our measure in radians is 2 pi. So again, if we want to solve for theta sub r, we'll multiply both sides. Whoop, I wanted to change color. We'll multiply both sides by pi again, so that they cancel on the right-hand side. And what we're left with is that theta sub r is equal to, and our degrees cancel as well on the left. This should be a unitless measure when we're done. Negative 135 pi over 180. And if we reduce that, I believe that is negative 3/4. I know I did this one earlier. Yeah, negative 3 pi over 4. So So that one reduces in a somewhat surprising way. But there we go. So negative 135 degrees is the same as negative 3 pi over 4 radians. Okay, so that was converting from degrees to radians. Now we want to convert from radians back to degrees, which the algebra on this can seem a little bit weird. So if there are questions on any part of this, please let me know. But we're just going to set up the same proportion that now it's theta in degrees that we're looking for is to 180 degrees. I'm just putting a visual separator there. And that's going to be equal to our measure in radians, which is pi over 12, over pi. Now, what we want to do is multiply both sides by 180 degrees. I need to get my degrees on there. So that is what we will do. We will multiply both sides. Come on, switch colors. There we go. By 180 degrees. We're doing that, so on the left-hand side they cancel, and we just have theta in terms of degrees. On the right-hand side, these pi's will cancel, so maybe there's a little funky algebra going on there, but think about that. Taking the reciprocal of the denominator and multiplying would put a pi next to 12, and then the pi's would cancel. But just canceling the numerators there, the numerator with the denominator is kind of the shortcut. And then we're going to have 180 degrees over 12, which is going to give us 15 degrees. So there we go. We've converted pi over 12 into 15 degrees. And hopefully that makes some sense, because we learned earlier that pi over 6 is the same as 30 degrees. And so if we cut pi over 6 in half, we would get pi over 12. And if we cut 30 degrees in half, we would get 15 degrees. So just another way to think about getting that one there. Okay, for the last one here, we have negative 4 pi over 3. We want to convert this to degrees, so we'll set up our proportion here. That 180 degrees is to, theta degrees is to 180 degrees. What negative 4 pi over 3 is to pi. So we'll do like we did before. We want to multiply both sides by 180 degrees. So that on the left-hand side, they cancel, and we're just left with theta in terms of degrees. On the right-hand side, these pi's again will cancel, and we'll be left with negative 4 times 180 degrees all over 3. If we plug that into a calculator, we would get negative 240 degrees. So there we go. That is more or less the way to convert from degrees to radians or radians to degrees. There is some other ways to think about this, some kind of different formulas of multiplying by either pi over 180 or 180 over pi, and that works too. But I also think that just looking at this proportion is less to memorize, and hopefully a natural proportion. I think that this makes a lot of sense once you get there. All right, next we will talk about coterminal and reference angles. So I'm going to kind of bounce back and forth between the definition and the example here so that we can make as much sense as possible. So a coterminal angle, or coterminal angles rather, there needs to be two of them in order for this to make sense, are two angles in standard position. So here we have a couple of angles in standard position. We've got this one in pink, and we've got this one in green, and if you notice, they share a terminal side. They are coterminal. Hopefully that word makes sense now. Since they share this terminal side, they are coterminal angles. One has a positive measure, one has a negative measure, but they have the same terminal side. And then a reference angle, an angle's reference angle, so this isn't comparing two angles, but we're saying each single angle has a reference angle, and it is the smallest acute angle that we'll call theta prime. So if you see any sort of symbol with a little apostrophe on it, we would say that it means prime. I just wrote F prime there. Once you get to calculus, that might mean a lot more to you. But we get this reference angle by looking at the the smallest acute angle formed with the terminal side of the angle we're looking at and the horizontal axis. So for the one that we're looking at here, let me just get rid of some of those other markings. For both of angles here, since they share the same terminal side, we're just looking for the closest x-axis here, or the horizontal axis rather, in case it's some variable other than x. But here that's just 45 degrees. So if we're just looking back, we're just mapping straight back to the closest horizontal axis, we get an angle of 45 degrees. So I just have it summed up at the bottom here that 225 and negative 135 are coterminal angles, since they have the same terminal side, and they both have a reference angle of 45 degrees. You might be thinking, who cares about coterminal angles or reference angles? Well, what we were seeing earlier was we were kind of focusing on some common angles that pop up. And once we know something about all of these common angles, then we can apply it to lots of other angles. And knowing that two angles have the same reference angle means you know a lot about all of those angles. If you know that two angles are coterminal, then you know a lot about all of those angles. So that's why we care about coterminal and reference angles. So let's do a little bit more with them here. We'll take a look at an example. For each of these below, I want to find a coterminal angle in the interval from 0 to 360, which means just one revolution. We'll see some of these here have several revolutions as they go around. So we just want to think just between this first interval from 0 to 360 or from 0 to 2 pi, whether we're talking about degrees or radians. And you can see that for the degrees, we are including 0 degrees and we are not including 360. Since those are technically the same number, we're saying that if you get to 360, just call it 0. And same thing with the radian measures here. We're saying that we are including 0, but we are not including 2 pi. Since they have the same measure, we need to pick which endpoint we're going to include, and we're including the left endpoint as 0 for both of these. So after we find the coterminal angle in kind of these first one revolution intervals, then we'll find the reference angle for each of these. So let's take a look here. Just get rid of my scribbles. Okay, so we have theta equals 960 degrees, which is way more than 360. So let's think about what's going on here. I'm just going to put some axes. We're going to start on our initial side, which is always the x-axis, the positive side of the x-axis, and we'll just think about making some revolutions around here. So if I go around one time, that's going to give me 360 degrees. If I make another revolution around, that's going to give me 720 degrees. If I go another 180, that's going to give me 900 degrees, and then I just need to go 60 more, which is another 2/3 of the way around. So somewhere around there, and then I'll draw my angle. So there it is. Here is the angle of 960 degrees. What we want to do is figure out the coterminal, so it has the same terminal side, but it is in between 0 and 360. So the way that we can do this, one way we kind of, I don't want to say cheated because we did the work here, but we know that we're starting with 960 degrees, and I want to subtract off 2 full revolutions. So I'm going to subtract off 2 times 360 degrees, because we made 2 full revolutions around before we hit our last side here. So this is going to give us 960 degrees minus 720 degrees, which is 2 full revolutions. That's going to leave us with 240 degrees. Okay, so we've got our coterminal angle. So 240 degrees and 960 degrees have the same terminal side, but I think that 240 degrees is going to be a more tangible angle for you to deal with in the future than 960 degrees is. Now we want to find the reference angle, which is the shortest distance, whatever angle is created by finding the shortest distance to the horizontal axis. So here, this is going to be an angle of 60 degrees, and I want to make that theta prime of 60 degrees. So here theta prime is equal to 60 degrees. There is our reference angle. All right, looking at this next one here, we want to find a coterminal angle to, let me switch back to yellow, to negative 225 degrees. That is in the interval from 0 to 360. So if I think about how this looks, I'm going in the negative direction. That's negative 90, negative 180. Negative 225 is going to be another halfway around there, another 45. So it looks something like that. So here is our angle of negative 225. We want this to be a positive value. So what we're going to do is think about moving back in the positive direction and making one full revolution until we get back to where we started, and now we should have a positive value. So what I'm saying here is if we're at negative 225 degrees, we need to add one full revolution to get back around. So if we do that there, we're just going to do negative 225 plus 360 is going to give us 135. So this is the coterminal angle, 135 here. I shouldn't call it theta because theta is already the name of the original angle, but that coterminal angle is 135 degrees. All right, now if I want to find the reference angle, we're just going to move the shortest distance to a horizontal axis, which is that way over there, and this is 45 degrees. Oops, not 40, but 45 degrees. So here we have our reference angle of 45 degrees. And we'll be using reference angles more later on. Right now we're just finding them, which seems like cool trick, bro, but we will be using them later on. So coterminal angle in the interval that we're asked, 135 degrees, and we've got a reference angle of 45 degrees. All right, now moving on to the radians here, and these are maybe a little less intuitive because we've just learned about them, but let's draw some pictures here. Pictures always help me a ton. So I want to go to negative 5 pi over 6. So if I just move 1 pi over 6 at a time, I can find negative 5 pi over 6. So if I think about moving a third of the way, that's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So 5 pi over 6 lives right around there somewhere, and I can fix my little drawing a little bit. But I was just counting by pi over 6s around until I found negative 5 pi over 6 being that angle there. So we want to do much like we did on the last problem where that is a negative angle. I need to get back into positive between 0 and 2 pi now. So if I add a full revolution back to this, I should get back to the interval that I want. So if I start with negative 5 pi over 6, and I want to add one full revolution, and one full revolution in radians is 2 pi. So I'm doing negative 5 over 6 plus 2 pi, which I could write that as plus 12 pi over 6, getting a common denominator there. And this is going to give us 7 pi over 6. So now I know that the coterminal angle in the interval from 0 to 2 pi is 7 pi over 6. Now I want to find that reference angle. So again, we're just moving closest way back this way. And this reference angle is going to be 30. Oh, I don't want to do it in degrees, but pi over 6. If I go one more pi over 6 in that direction, I would be at the x-axis again, or the horizontal axis, I should say. So there we go. We've got that one now. The coterminal angle is 7 pi over 6, and the reference angle is pi over 6. Okay, for the last one here, I want to figure out what is coterminal in the interval from 0 to 2 pi with 13 pi over 2. So let's figure out where 13 pi over 2 is. So we're just going to count by pi over 2. So remember that a single pi over 2 is just 90 degrees. So there's 1 pi over 2. There's 2 pi over 2. 3 pi over 2. 4 pi over 2. 5 pi over 2. 6 pi over 2. 7 pi over 2. 8 pi over 2. 9 pi over 2. 10 pi over 2. 11 pi over 2. 12 pi over 2. 13 pi over 2. So we've traveled all the way around and we ended back up where hopefully we already know that that is just pi over 2 since we counted by pi over 2s. So without doing much work, we can already tell that the coterminal angle is pi over 2. But I want to do this in a more of a legit way with showing all the details here, because if we have some value that's not by pi over 2s, but this was instead 2 pi over 13, we wouldn't be able to do this in quite the same way. But I did see that we made how many full revolutions around? We made 1, 2, 3 full revolutions before we win another pi over 2. So what I'm going to do here is take 13 pi over 2, and I'm going to subtract off 3 full revolutions. So a full revolution is 2 pi. So here I've got 13 pi over 2 minus 6 pi, and I could write 6 pi as 12 pi over 2. Just getting a common denominator there. And then when I subtract, I just have 13 pi minus 12 pi is just a single pi over 2, which as predicted is what we got. And then if I want to find that reference angle, well, we need to go back to the closest x-axis, and you could really either go either direction. That is a distance of pi over 2, or that is a distance of pi over 2. So here the reference angle is also just pi over 2. So there we go. We have a bunch of different examples of finding coterminal and reference angles. In general, I just think about how many more revolutions we have to go here. Technically, actually, if I'm looking for 960 and I'm not drawing things out here, what I would do on a calculator is just put in 960 minus 360, because I know that's a full revolution, and just start pressing equals until I get some number in the interval that I want. So that is maybe a short method that we can talk about later to do these, but here's a lot of detail shown out here. So yeah, there are coterminal and reference angles. All right, next we'll talk about arc length here. So this is just kind of an addendum to this section, but since we defined our radian as the ratio of the arc length to the radius, that means that we also have a relationship to find the arc length, and that is to just multiply it by the radians. So if you want to see the algebra here, it's not too difficult. We'll take the formula that we already know, and we'll multiply both sides by r, so that the r's cancel, and then we are left with what we wanted. So a pretty quick formula derivation there. So let's take a look at a couple of examples. We'll see this in action, and then we'll do a bigger application problem here. So first we have a circle with a radius of 10. So I'm just going to sketch this in here and see if we can't get a picture going. I think that I'm a very visual learner, so I like drawing pictures. And we have a circle that has a radius of 10. So I'm just going to sketch a circle in here and maybe try and do a better one than that. So there's our circle. And we know that the radius is 10 feet. And we have an angle measure of 2 pi over 3. So where is 2 pi over 3? The way that I'm going to count this is by pi over 3s. I know that I've got 1 pi over 3 there. If I go another pi over 3, that's going to be about there. So I've got this measure, this angle measure of theta equals 2 pi over 3. Well, we didn't necessarily need to draw this picture in order to do this problem, but I did want to give some intuition what we were finding, which is this arc length right here. We want to know, what is this distance? And since it's curved, it's a little bit harder to find. But we know from what we just saw above that if I want to find this distance s, that is going to be the radius times the angle measure in radians. And I'm being super clear that it's radians here. I didn't write it above, but we were using the definition of radians. So hopefully it's clear that this angle always needs to be in radians. If it's not, then we need to make a conversion first. Here we're given in radians. So we've got 10 feet times a radian measure of 2 pi over 3, which is going to give us 20 pi over 3, which is about, I think I wrote this down somewhere, 20 pi over 3 is about 20.94 feet. And that actually makes a lot of sense because pi is about 3. 3 is 3, so it's not too surprising that we found something pretty close to 20 as our final result there. So there we go, just using a quick application there to find arc length. Here we are going to need to do a little bit more work. So here we have a circle with radius 15. So let me draw this circle in. Here we've got a radius of 15, perfect. And an arc length that subtends a central angle of 105. Central angle just means that we have a standard angle, that it's centered on the vertex, or the origin here. So 105 degrees, well, it's going to be like, I don't know, kind of around in the same spot. It's not exactly where the other one is. But it's a little bit more than 90, right? It's a little bit less obtuse than the last one. So before we can do this, we need to get the angle measure in radians instead of degrees. So we're going to set up that proportion that we looked at earlier. 105 degrees is to 180 degrees. What the measure in radians is to just pi. Remember that 180 degrees and pi are the same measure. So here we will multiply both sides by pi. They are going to cancel on that side. That's the whole reason that we did that, so that we get the radian measure. Here the degrees cancel, so we have unitless measure of 105 pi over 180. And that reduces to 7 pi over 12. So here is our radian measure. Now we can plug things into our formula. We're going to get that this distance here, S is equal to the radius times the radian measure. Here the radius is 15. The radian measure is 7 pi over 12. If we multiply those together, we should get that it is about 27.49, and here we did centimeters. So I guess that seems about right, just comparing these two results here. The angles were about the same, and the fact that the second radius was larger meant that it traveled a little bit more of a distance, even though the angle wasn't quite as much. They were still pretty close. So yeah, I feel good about these answers here. So that is how we can use knowing the radius and the measure of the angle in radians or degrees to get the arc length. All right, here is a final application problem using what we just learned about arc length in order to answer this question. So we have the minute hand on a wall clock is 30 centimeters, and the hour hand is 15 centimeters. In fact, I don't think that we're going to do anything with the hour hand on this one. I decided to just focus on the minute hand for this one, so we'll take that off. But we know that the hour hand rather, the minute hand is 30 centimeters. So let's just take a look at what this looks like. I'm just going to put a little clock face here on some coordinates and look at that and what we're saying here, and let's kind of readjust, and we'll make this what we're fixing for this one. And you could like maybe turn that, rotate it, and think about things in terms of being on the axes, but I just wanted to think about this as being a clock here. So here's our minute hand. I'll maybe do it in green, and that is going to be a length of 30 centimeters. And what we're asked for is how far the tip travels here as it starts traveling around in 77 minutes. So we're just going to start at the top here. I suppose we could start at the 15-minute mark and make it line up with the horizontal axis, but I think this should still make sense. So we want to know how far it's traveled in 77 minutes. So how many rotations does it make in 77 minutes? Knowing that rotation will tell us what our radian measure is. So if we think about traveling all the way around here, well, that's going to go around 60 minutes, and then it's going to go, so that's one full revolution, that's 60 minutes, so we already know that we're more than a revolution. We're going to go 15 more, and then a few more. So we're going to be down here. That is what the angle is, the terminal side, but we have made a full revolution and a little bit more as it's done this. So how many revolutions has this made? It has made 77 over 60 revolutions. And we're going to use that in order to figure this out here. So if I want to know how many radians this is, then I can do however many revolutions we made times the number of radians per revolution. So this is, again, revolutions. This is radians per revolution. Will just give us radians. So we can write this, those will cancel, and we'll have 30. So we'll have 77 pi over 30. This is the number of radians that we've traveled around here. And now I think we should be able to figure it out. We know that the distance it has traveled should be the length of the radius, which in this case is 30 centimeters, multiplied by its angle measure in radians, which is 77 pi over 30. Well, how about that? The 30 and the 30 cancel out, almost like I designed it that way. And we're left with just 77 pi centimeters, which if we convert that, will get us, I thought I did this at some point and wrote it down, but I guess I didn't. So let me pull out my handy, oh, I did have it. It's about 242 centimeters. I did convert it. So there we go. The distance that this has traveled as it went around was 242 centimeters. All right, and I think with that, it is time to practice. So I wish you well. Good luck with the homework. If you have any questions, please let me know, and I will see you in our next video.